In lesson 2 of this module, we're going to talk about using counting techniques to solve probability questions. So we're not introducing any new formulas, we're really just taking combinations and permutations and using those to help us calculate probabilities of events occurring. So we will look at 4 examples here. The first example, 4 students from the VLC make it to the Provincial Business Championships. There are 50 students in that competition, so we need to figure out the probability that students from the VLC will finish in the top 2 spots. So we're always going to go back to the standard probability formula, which is nothing complex really. It's just basically once you have an event, the probability of that event occurring is the number of ways that it can occur divided by the total number of possibilities, or the number of outcomes in our sample space. So to start with, we need to identify what exactly is the event here. So if we're trying to figure out the probability that students from the VLC finish in the top 2, then that event is VLC students finishing in the top 2. So how many ways can that occur in the top 2? So the number of ways that can occur, well, there are 4 students from the VLC in the competition, and this basically amounts to choosing 2 out of those 4 to fill that spot. We could list the students maybe A, B, C, and D and give them those letters and then rearrange them and choose 2 at a time and write down all the combinations, but we know that that amounts to taking 4 objects and choosing 2 of them, in this case 4 students and choosing 2 of them. So we can use combinations to determine the number of different outcomes. And then also for the sample space, if we look at overall there being 50 students in the competition, well, if we're looking at the top 2 positions, then that means we're choosing 2 out of those 50 if we're just looking at a snapshot of the finalists. So choosing 2 out of the 50 students can be used to represent that the number of items in the sample space. So we can go ahead and calculate these then. So if we've got 4 students and we choose 2 of them, that's 4 factorial divided by 2 factorial twice over. That just ends up giving us a 3. So we have 3 out of 50 choose 2. So 50 choose 2 is 1,225. Now, in fact, I think I've made a little bit of a mistake here. 4 factorial divided by 2 factorial twice is actually going to give us 6. There we go. 6 out of 1,225. And that's it. So we don't need to consider 3rd place, 4th place, anything like that. We're just considering the top 2 positions, and we can generate a probability of that event occurring. All right, so the next example, let's consider a test that is a true-false test with 4 questions. So we're going to assume here that we're going to guess random answers for each one. So let's say you have no idea about the correct answers for the test, and you're simply just guessing at this point. Now you've answered questions similar to this in the past. Now this, however, we're going to answer from a probability perspective using combinations. So the first part is, what's the probability that we get 25% on the test? Well, that in itself is our event A. So getting 25% on the test. So now we need to think about, all right, well, if we want to figure out the probability of this event occurring, it's the number of ways it can occur divided by, once again, the number of items in the sample space. So if you think about the number of ways you could get 25% of the test, think about the number of outcomes that would result in a score of 25% or 1 out of 4. So we could once again go ahead and list these if we wish. We could say, okay, well, I get the first one right, and then the next 3 wrong. And that's a possibility. So let's say I represent that using a check mark and 3 X's. And I could keep on doing that, except maybe instead of getting the first one right, I get the second one right. Or I could get the 3rd one or the 4th one. So here I can list out those 4 possibilities, but ultimately, once again, this just amounts to determining, we've got 1 correct answer here out of the 4, so you're just choosing where to sit that correct answer. And it amounts to choosing 1 out of 4 placements for the correct answer. So the number of ways that can occur is simply 4 choose 1. Now, the number of total outcomes in this case, well, if there's a true-false response for each question, and that means there's going to be a true-false answer for each question, this doesn't necessarily model a combination or a permutation calculation. In fact, in this case, if you think how you'd model all the possibilities of a test, we have done this before, And if you think about each question kind of being a level, you can model this using a tree diagram. So we could say that the first question could be true or false, and then from there we have the second and the third and so on. So if we did 4 of these levels, so to speak, and each level is going to have 2 branches coming from it, because there are 2 possibilities, we can determine the total number. So in this case, we could count the paths to the bottom, or notice that it's just going to be kind of a similar formula to what we've used before. We have 2 to the power of 4. So 2 to the power of 4 in this case represents making 4 selections where each one has 2 possibilities. So 2 to the power of 4 is 16, 4 choose 1 is 4, and so we can simplify that as 1/4. So there is a 25% chance to get 25% on the test. Now, sounds very straightforward and easy, however, the calculations were necessary to verify. So for part B then, to pass the test, we need to think about what different events fall into this category. We talked about different events and how they likely have different probabilities of occurring. Well, passing the test, we know that getting 25% doesn't fit into that. If you think about there being 4 questions, we know then that out of those 4, we could get either 2, 3, or 4 correct. So the other option, we've talked about the kind of the direct method. We can go calculate each of these in the same way that we did for part A, or we could look at this using the method that we were already introduced to in the first lesson, and that is to use the complement of a set. So rather than making these 3 calculations, I could simply say that, let's say I said that this event was called event B. Well, I could say then that instead of just calculating the probability of passing the test outright, I could say that that's just 1 minus the probability of failing the test, which would be the complement of the original. And I know that failing the test means that I either get no correct answers or 1 correct answer. And we've already done the calculation for 1. So to calculate this then, I could say, well, I'm just going to take 100% and subtract the probability that I have 1 or 0 correct answers. And that is what represents B prime, or the complement of B. So the probability that I have 1 or 0 correct answers, when we already calculated the probability that we have 1 correct answer, right, that's just the probability of 1 correct. That's our answer from part A. Our answer for the other one is just a quick calculation that we need to do separately. So the probability of getting 1 correct answer here, well, we said that that was 1 out of 4. So in other words, 25% maybe makes a little more sense if we represent this as a decimal. 0.25, there's a 25% chance of getting 1 correct. And the probability of getting no correct answers, whether we use the tree diagram or counting techniques in this case, ultimately you should get to the same result. It's really just 1 out of those 16 possibilities. There's only one way to get no correct answers, and that's if you get them all wrong. So in this case, it's 1 out of 16, or we could once again express that as a decimal if we wish, 0.06. So we can calculate then the probability of passing the test is, if we're not going to fail it by getting 0 or 1 right, all of the others are going to fit into that category of passing the test. So 1 minus those 2 values gives us 0.79. Or there's a 79% chance. And I've made a small mistake in my math. That should be 0.069. So a 69% chance. Okay, so we can look at that indirect method using the complement of the set. In some instances, to save us a little bit of time. Here, it maybe isn't going to save us a lot of time, but you could imagine if we had more questions, or possibly more than 2 options for each question, that this certainly would be a time-saving technique. Okay, so example 3 then. I've been asked to pick 3 of my senior students to win VLC Student of the Semester. In this instance, we have a situation where we have more than one category. And so rather than drawing from the same pool of items, we've got to look at different categories of items. So I have an MDM4U, a data management class with 23 students, and a computer science class with 13 students. So if I'm going to pick 3 of these, what's the probability that all of the students will be selected from the data management class? Well, once again, we can identify here, this is the probability of an event occurring. So we'll call this event A. So for part A, the probability of that event occurring is once again the number of ways that that can occur, number of outcomes divided by the total number in the sample space. So we've got to think here in this instance, well, the number of ways that all the students could be selected from the data management class. So I'm picking 3 kids, and if they're all from that class, that means there are 23 that I'm choosing from. So I could pick any 3 of those 23 students, and that would represent an outcome in this event. So I have 23 to choose from, and I'm picking 3. That represents the numerator. Now, the denominator is the total number of ways I could pick 3 students, not necessarily all from one class or all from the other class, but really just any students in general. So I ignore the classes then at that point, and I say I've got a total of, well, in this case, I've got 23 in one class, 13 in the other, so I've got a total of 36 students, and if I'm going to pick 3 out of those 36, then that just amounts to that expression, 36 choose 3. So we're assuming here that there's no overlap. If you think back to Venn diagrams, that the intersection is empty, no students are taking both classes, then this is what it amounts to. So 23 choose 3, we can calculate that to be 1,771, and 33 choose 3 is obviously going to be larger, 7,140. So for part A, this boils down to about a 25% chance or likelihood that all students will be from the data management class. So then for part B, well, we've kind of generated a process here. We know we can select students in certain ways using this combination formula. Well, before we go ahead and think about this situation that at least one student will be selected from the ICS4U class, we could think of that as being, at least one means that we could have 1 or 2 or 3 out of the 3 kids. Now, if you think for a moment, that indirect method comes in really handy here, because rather than doing 3 calculations, notice that the answer to the part A was really the case that 0 students were from ICS4U. So that was the 0 case, and that was event A, right? If they're all selected from the data management class, that means none of them are selected from the ICS class. And so this is the complement of the set. At least one student means you're not taking no ICS4U students, you're taking at least one of them. It means you're not taking all data management students. So we could actually just jump to this. If we call this event B, the probability that we have all, or rather at least one ICS4U student is 1 minus the probability that we have no ICS4U students. And we actually calculated that probability above. That's the same as the probability that we have all MDM4U, which is just the probability of event A occurring. And we said that that was 24.8%. So we have a 75.2% chance of this occurring. All right, so those are 3 extra examples for you to consider when looking at how to use combinations and different counting techniques within solving probability types of questions.